Thank you, Stan. That is definitely a singular introduction. Okay, well, look, thank you very much. Can people hear me on the other side of the various phones and Evos? Take that as a yes. Well, thank you again very much for inviting me here and for this visit. So far it's been almost a month and a half, and I'm enjoying it a great deal. It's very nice to be back. And thank you also very much to all of you who have come to the talk today. As Stan said, the talk is about gravitational waves from accreting neutron stars. And the work that I'm going to describe has been done by predominantly by these people here who are PhD students at the School of Physics at the University of Melbourne, with the exception of Carl Vetter, who some of you may know, who's from the ANU but collaborating with us. Our emphasis, as Stan said, has been actually not on the fringes of the gravitational wave community theoretically. We've been very interested for quite some time in the physics of the sources themselves, but as Stan correctly pointed out, we haven't been involved in data analysis very much at all to date. And later in the talk, I'll mention the one little project that we've started in the data analysis area. My student Christine Chung, who's listed up there, is working with the people at the AEI to look for a certain class of sources that I'm going to describe, that I'll describe. But the majority of today's talk will be the theory of the sources. Those of you who may have heard me speak briefly at the Tapir seminar about gravitational waves from non-axisymmetric blocks of superfluid within a neutron star have a lot of kind of physical uncertainties. It's a very interesting problem. Apart from anything else, but the physics of the motions of the superfluid and the physics of the neutron star itself, interior, is uncertain. And consequently, the strength of those signals is also uncertain. And our estimates so far have been that although they're very interesting, they're likely to be on the weak side. By contrast, what I want to talk about today, gravitational waves from accreting neutron stars, is much more optimistic in terms of the strength of the signal. This type of source is actually viable for detection with advanced LIGO. May not be the first thing that's seen, but it is one of the strong possibilities. And the underlying physics, although it's subtle, is not uncertain in the way that superfluid motions inside neutron stars are uncertain. So it has a slightly different flavor. Okay, well, for a while now, and in a moment I'll remind you why we think so, it has been believed that X-ray binaries are potentially strong periodic kilohertz sources of gravitational waves. And if this is true, then they have some advantages over things like neutron star inspirals because they are persistent, not transient. Very often, from electromagnetic observations, you know crucial parameters like the spin and the orbit of the star, and you are therefore able to fold the signal coherently and do much better in terms of your signal to noise. And for the most part, people suspect that the signal from these sources is relatively simple. I say sinusoidal, but in quotes, because as I'll show you during this talk, there are some wrinkles to that, some complications, which are both interesting from a physical point of view, but also a bit of a nuisance from the detection point of view. We'll see what that is. Now, in these objects that lead to gravitational radiation. And they include things like radiation reaction-driven instabilities, like the classic CFS instability for R modes, thermocompositional non-axis symmetries around the star, which come, for example, from nuclear processes like electron capture occurring at different rates at different points on the neutron star surface. And the size of the quadrupole from these various mechanisms is, of course, determined in part by the equation of state of the star. If you have strange quarks, for example, within the star, then you get potentially larger quadrupoles than you might naively expect. And there has been interesting work by Ben Owen and others on that topic. In this talk, I'm not going to mention these other mechanisms any further, not because they're not viable or interesting. They are very interesting, but because I want to focus on the work that we've been doing at the University of Melbourne, which exploits the one known non-axis symmetry of a neutron star, and that is its magnetic field. And I'll show you how that magnetic field can lead to quadrupoles that are potentially large enough to be detected. Okay. First, just to remind you, by way of review perhaps more than anything else, that there is already indirect but reasonably compelling observational evidence that accreting neutron stars are sources of gravitational waves. And that evidence comes from a class of systems known as low-mass X-ray binaries, where you have a neutron star accreting material from a low-mass companion, say a red giant star, via an accretion disk. Now, the spins of the neutron stars in these systems can be measured in two different ways. Firstly, directly from the X-ray pulses that are emitted by that neutron star. And secondly, indirectly, by detecting millisecond oscillations in the X-ray light curve following thermonuclear bursts, which sort of recur quasi-periodically on the surface of these objects. These are like thermonuclear explosions which spread over the surface of the star. And in a couple of objects, including this famous one here, the pulses and the millisecond oscillations in the tail of the thermonuclear burst are seen simultaneously and at exactly the same frequency. And that, therefore, gives us confidence that when we're looking at these burst oscillations, we are seeing a faithful proxy of the spin period of the star. The right-hand plot there shows a rough histogram of the spin periods of the objects that have been measured to date. There are some more which are not included. That's about a year old, but it still gives you the idea. And you can see from that histogram two important things. Firstly, the spins are clustered in a fairly narrow range, from 200 to 700 hertz. Secondly, there's a distinct gap, distinct cutoff at 700 hertz, and that cutoff lies well below the standard estimates for the centrifugal breakup frequency of these neutron stars. Now, that breakup frequency does depend on the equation of state, which, as I said before, is unknown. But for most reasonable equations of state, it's round about where I've drawn it with some range. And that gap is statistically significant and certainly there. In fact, if you do a careful analysis, which Chakrabarty and others did in 2003, you can show with a simple Bayesian argument that that gap is there at a high level of confidence. And that statistical argument depends just on two very weak priors. The first is that you have a roughly uniform distribution of spins to the left of the cutoff. And the second is that you have no objects spinning faster than 3 kilohertz, which is almost certainly true. Okay, now what might explain that gap? One sort of thing to suspect might be that accretion doesn't push them that far. But our understanding of accretion mechanisms really doesn't allow for that possibility. Accretion, in most of these objects, they might accrete maybe 0.1, 0.5 solar masses of material. That is definitely enough to push them to centrifugal breakup. And so in 1998, Lars Bilston made the very interesting suggestion that if these objects are non-symmetric, they have a quadrupole moment, then the gravitational radiation emitted by that spinning quadrupole will exert a spin-down torque, which is enough to balance the spin-up torque from the accretion. And if that balancing, if that stalling is to happen at 700 hertz, or thereabouts, then you need a quadrupole moment of 1 part in 10 to the 8. And this, of course, is an interesting number because if that quadrupole moment exists, as I'll show you in a moment, these are potentially interesting sources for advanced LIGO. Small note, this estimate, of course, depends on an estimate of the accretion torque, which in turn depends on the lever arm over which that accretion torque is exerted. And in the past, Lars, for example, made that estimate using a lever arm which equals the radius of the star. In fact, these stars have magnetic fields, and the correct lever arm to use is the radius of the magnetosphere, not the physical radius of the star itself. And that gives you an extra factor of 2 or 3 to the power of 1/4, which is not much, but in the context of something like detectability by LIGO might be important because it raises the quadrupole by a proportionate amount. Okay, this excuse me, this diagram here illustrates our best guess at the detectability of these sources. It has been put together by Anna Watts and Badri Krishnan in a paper published this year. What you're seeing here is the wave strength on the vertical axis and the gravitational wave frequency on the horizontal axis. And on the diagram, we see 3 different objects being plotted. The blue squares are accreting millisecond pulsars. The green triangles are bursters, neutron stars which burst, as I described before. And the red inverted triangles are sources which contain the so-called kilohertz QPOs, quasi-periodic oscillations in the X-ray flow. The open symbols indicate that the frequency of the source has not been confirmed. And in the case of the QPOs, we don't, unlike for the other 2 classes of object, we don't have a direct measure of the spin frequency. So to draw this plot, these authors have made an estimate of that spin frequency based on the midpoint of the separation of the QPOs that is measured. Now, that is just a proxy for the spin frequency in those objects. It may not be the spin frequency. In fact, there are good reasons to doubt that it is, but that's how this plot is. Also superimposed, we have noise curves for different interferometers, initial, enhanced, and advanced LIGO, broadband, and narrowband, and then something a little bit imaginative, the ET. And the plots are constructed for an observation time of 2 years. And you can see that, at least for the later generations of interferometer, there is some prospect of seeing these sources. However, it's important to understand that this is the most optimistic estimate for detection, and it is presented as such in this paper. Okay? It's optimistic in the sense that they're using single templates and integrating for 2 years. Now, for accreting millisecond pulsars, for example, we know that that's impossible because you only see them for 2 months when they are in outburst, and then they peter away, and you lose, of course, phase coherence. You have no idea what the ephemeris is doing. So, in a sense, that's a unreasonably optimistic estimate. You can, of course, do semi-coherent searches on those objects, and people have talked about that. If you do that, then you will have many templates, and the signal-to-noise ratio that you demand goes up, or square of it goes up from 11 to 25 or 36, depending on how you want to count it, and that will tend to bring the points on this graph down a bit and therefore reduce the detectability. The plot is constructed assuming that the accretion rate is proportional to the average X-ray flux from these accreting sources. That may or may not be sensible. It's not clear, but you could instead use the X-ray flux during outbursts to measure the accretion rate. That will tend to multiply by a factor of 2 or 3 the wave strain that you get. But of course, the outbursts only last for a short time, months. And so the total observation time that you have during an outburst decreases. And so it's not clear how those two effects will play off against each other. Okay, so that's the state of play in terms of potential detectability. Now I want to talk a little bit about one possible way of creating these quadrupoles that are inferred from the spin frequency data that I showed you 2 slides ago. And as I said before, that method is to exploit the one known non-axis symmetry in a neutron star, namely its magnetic field. Now the first point to make, and it's a very important one, is the magnetic field in and of itself, if it's just a nice dipole with 10 to the 12 Gauss, is completely insufficient to make a quadrupole of any reasonable size. So if you have a 10 to the 12 Gauss dipole field, you will get hydromagnetic perturbations of 13, which is too small for LIGO to see. But the crucial point of this talk is that the picture is actually more optimistic and more complicated. Because although the field is too weak when it is undisturbed, it has the effect of channeling the accreting material onto the poles of the neutron star. And that channeled flow will, as I'll show you, distort the magnetic field substantially and strengthen it at the same time in certain places in a way that does produce a quadrupole that is relatively large. So how does that happen? Well, imagine your neutron star with initially a dipole magnetic field and an accretion disk somewhere out here. As material flows out of the accretion disk and onto the star, it is funneled, as I said before, by the magnetic field onto the poles, and therefore you start to build up a little mountain of material at the poles. Now clearly, that mountain is going to slide sideways under its own weight. And as it does that, it drags the magnetic field lines with it, because remember, this is highly conducting material. It's a hot plasma, which to 0th order is perfectly conducting. And in a hot plasma, the magnetic field and the material are frozen together. You have the conditions of what is called ideal magnetohydrodynamics, and the field and the fluid the field is frozen into the fluid. So the mountain slides sideways, drags the magnetic field lines with it. That has the effect of compressing the magnetic field towards the equator. So now the field is stronger, and it pushes back on the mountain so that a new equilibrium is reached. You can see that in the picture here. What you're seeing is the neutron star with altitude logarithmically plotted against on both those axes. The material is flowing into the magnetic pole. The solid curves are magnetic field lines. The dashed contours are density contours. And you can see that the density contours are piled up at the magnetic pole, and the magnetic field has been pushed sideways and compressed as a result. Now, you can calculate, in fact, the structure, the exact hydromagnetic structure of that so-called magnetic mountain. And it's just the solution to this equation, where you have here, this is a force balance equation, you have the Lorentz force, the gravitational force, and the thermal pressure all adding up to 0. It turns out you have to be careful when you do that, because there are an infinite number of solutions to that equation. And that's because that is a steady state equation. It contains no information about how you get to that final state from a given set of initial conditions. So you need a supplementary condition to pick out the one correct final state from that infinity of possibilities. And the way you do that is to require that in the process of going from your initial state to your final state, material does not cross magnetic flux surfaces. Right? That's just another way of saying that the field and the material are frozen together as you expect in a perfect conductor. And that translates into a condition on this line integral here along all of the field lines, where this is the density and this is the magnetic field strength, which just in turn translates to saying that the mass that's shaded between those two flux surfaces in the plot, which is shaded in red, is constant throughout the accretion process, except for whatever component, whatever fraction of mass has been added between those fuel lines due to the accretion itself. Of course.
When you go through this distortion, does this in some way feed back to the source that's contributing the stuff that's flowing in?
It's a very interesting question. It does in the following way. It doesn't, not by any sort of disturbances propagating back along the field lines, because the speed, effectively the speed of those disturbances is too slow. But what, as I'll show you, what this does is reduce the magnetic moment of the star. And so as seen from the disk, you now have a weaker magnet. And that changes the geometry of the accretion as the accretion proceeds. So in that sense, it does. Okay. Now, as I said, solving these coupled, integral differential equations is not easy, but you can do it. And when you do it, you can calculate the ellipticity, the quadrupole moment of the magnetic mountain that you obtain. And what we find generically is large mountains, larger than 1 part in 10 to the 8. In fact, in the simplest, idealized version of the calculation that I've just shown you, perfect conductivity and everything else, we get mountains as large as 1 part in 10 to the 5, and we get that routinely, which is not good because, of course, a mountain of 1 part in 10 to the 5 would have been seen by LIGO already. But the idealized calculation can be done exactly, and when you do it exactly, that's the answer that you find, which is interesting. The second point I want to make just briefly is that, as I said before, the effect of this burial is not just to build a mountain and a quadrupole moment. It also reduces the dipole moment mu of the neutron star. And it does that effectively because it kind of combs away the field from the pole of the star. And of course, the field at the pole of the star is what determines predominantly the dipole moment. So you have a prediction here that as you add more material, you get a larger mountain and stronger gravitational waves, but you get a smaller dipole moment. And so you have a prediction there of an inverse correlation between wave strain and dipole moment, which in principle, one day, if this was ever detected by LIGO, could be tested.
Are these done in a post-Newtonian approximation or full GR?
No, excellent question, neither. They're done in purely Newtonian. There are many things, and you'll see this as I go through the talk, that we've left out. Turns out even this first version of the calculation is not an easy thing to do. So we've really tried to do it piece by piece. Including the GR, very roughly, will just change this potential for the purposes of this problem, by 40%. Or whatever it is for a neutron star, without, I would say, changing qualitatively the overall behavior. But as I'll talk about later, when we think about the time-dependent, the oscillations that this structure can show and that kind of thing, then the full GR, I think, is important. We haven't included. Say that again.
Perhaps if the full GR would have even a greater quadrupole.
I can't say. Very interesting question. We simply haven't calculated it. Okay, now this is just the mathematics of it, which I won't bore you with. the next, what I want to do next is talk about the stability of this mountain, because those of you who are a little bit familiar with plasmas and that sort of thing will know that distorted magnetic fields like that are unstable. But before I do that, I just mention that the original motivation for looking at this, as well as gravitational waves, was because, as many of you will know, there are two classes, broadly, of neutron stars that have been found. There are the ordinary pulsars, ordinary neutron stars with magnetic field of 10 to the 12 Gauss, and then there are the so-called millisecond pulsars that have magnetic dipole moments of 10 to the 8 Gauss. And this mechanism provides, as I described, a natural way of getting from a strong field to a weak field via accretion. This diagram illustrates that. What we're looking at here is the dipole moment on the vertical axis in units of Gauss, and the accreted mass on the horizontal axis in units of solar masses. There are four different kinds of objects plotted here. The solid boxes are low-mass X-ray binaries, like the ones we discussed before. The open boxes are high-mass X-ray binaries, which accrete via wind rather than a disk. These two here, these solid triangles, are neutron star, carbon-oxygen, white dwarf binaries. The ones above, neutron star binaries. And these ones here, neutron star, helium, white dwarf binaries. And the points are constructed there from a mix of observation and theory. So the magnetic field for the pulsars can be determined directly from their measured spin down. The accreted masses for all of the objects have to come from evolutionary calculations. And those evolutionary calculations are notoriously uncertain. Apart from anything else, even if you can calculate the mass that is lost by one of the stars in the binary, there's no guarantee that the mass transfer is conservative. You might only get a small fraction which is captured by the companion. And that fraction is not well understood. So the error bars in the horizontal direction, as you'll see, are quite wide, remembering that this is a logarithmic scale. Nevertheless, there is an overall trend of a decrease of the magnetic dipole moment decreasing with accreted mass. And the curves that you see there correspond to the predictions of our burial model. So the central one corresponds to an initial magnetic field of 3 by 10 to the 12 Gauss and an accretion rate of 0.1 Eddington. These two have the same initial field, but an accretion rate 3 times larger and smaller. And these two have the same accretion rate, but an initial magnetic field 3 times larger and smaller. The detailed agreement, it may or may not be promising. That's not really the point. The point here is to show that there is the overall trend, both in the observations and, as you expect, in the model I've just described. The outliers, which are circled there in light blue, all have other independent good reasons for being outliers. They have unusual evolutionary histories, and I'm happy to talk later about that if anybody's interested. Okay, now, as I said before, the main question that one might ask, confronted with the mountain I showed you, is whether it is stable. And there are two kinds of stability that we need to worry about here. The first is that when you have distorted magnetic fields, even in the perfect conductivity limit, those fields like to unwrap themselves into a less distorted configuration. And we know that's true. It's the reason why, after 40, 50 years, we still don't have a functioning magnetic fusion device. The second kind of instability, relaxation we need to worry about is through ohmic diffusion. Although the plasma is highly conducting, it is not perfectly conducting. And especially for a distorted magnetic field where the gradients happen over short length scales, you will expect some relaxation just because of ohmic losses in the material. The magnetic field is not exactly frozen to the fluid, but rather slides through it, again because the conductivity is not infinite. So we need to check what our mountain does in the face of these two effects. And what we've done in order to do that is take an equilibrium mountain, which we calculated as I showed you before, and load it into a code, a solver, which is called Zeus 3D. This solver has wide applications in astrophysics and a long history of usage, many tests and that kind of thing. And perturb the mountain slightly and watch it evolve. This slide shows you the punchline of those experiments, which sort of took a long time, but I can summarize them in this way. So what you're looking at here on the left is the same plot that I showed you before over here, but just redrawn in these rectangular coordinates. So this is altitude above the star, and that is latitude with the equator at the top and the pole at the bottom. The orange curves are isodensity contours. The blue curves are magnetic field lines. And you can see again the little mountain of isodensity contours at the pole. The quadrupole moment corresponding to this two-dimensional equilibrium is 3 parts in 10 to the minus 5. We then take that equilibrium, perturb it, load it into the code, perturb it, and see what happens. At the top right, we do that experiment while maintaining perfect conductivity. No resistance in the problem. And what we find is that, sure enough, the distorted magnetic field does relax to some degree. You can see that that's happened. But the mountain doesn't go away. The instability, which is a toroidal Parker instability for those who are interested, saturates, and it saturates at a quadrupole moment which is about half of what you started with. The lower panel on the right shows the opposite experiment where we do allow for some resistivity in the problem. And in this case, we've chosen for that resistivity the value that people talk about in the literature, which depends on electron-phonon scattering. There are some uncertainties in that value, but the uncertainties are maybe a factor of 2, maybe a factor of 3. And what you're seeing here is the result of that evolution after 1 billion years, which is a typical estimate for the lifetime of such an object. And you can see that, again, there has been some relaxation, as you would expect. But, again, the quadrupole has been reduced by 50%. Now, the difference is that if you keep running this for 2 times 10 to the 9 years, 3 times 10 to the 9, and so on and so forth, you will get more and more relaxation until eventually the mountain completely relaxes away. We know that if you have some resistivity there, then in the t goes to infinity limit, you will get complete relaxation of your structure. But over lifetimes that are relevant and interesting, and for resistivities that are relevant and interesting, the reduction is maybe a factor of 2. Okay. Now, just to show you some snapshots of the evolution, this is the case where you have no resistivity. So the relaxation is purely because the field lines want to straighten themselves out. What you're seeing here is 6 snapshots during that evolution. The orange bit is the mountain above a certain density. The blue and green are the magnetic field lines, the only difference being that the green ones were started from the equator and the blue ones are open and leave the pole. And you can see that over, I can't quite remember the time between these, but it's many Alfvén times, many dynamical times of the system. You do get some relaxation, but at the end, the mountain is still there, consistent with what I told you before. And for those who are interested, as I said, the relevant mode is an angular Parker submode, which we have identified via its growth rate and the growth of toroidal magnetic field in the structure. This briefly shows you the quadrupole moments, which make exactly the same point. You can see that there's a transient instability, but as it would be really good if it was a point, but it's okay. But as time goes by, the quadrupole settles down to about 40%, goes from 1.0 to 0.6. Let me make a point here which is sometimes confusing. Oh, thank you very much. Thanks. Which is sometimes confusing. These quadrupole moments are defined relative to the magnetic axis, okay, not to the rotation axis. So you might think, remembering that Q12 tells you about the non-axis symmetry, you might think that the non-axis symmetry has died away. Well, it has relative to the magnetic axis. But the magnetic axis is then in turn tilted off by 10, 20, 30, whatever degrees relative to the rotation axis. So you still have, from a gravitational wave point of view, a very interesting quadrupole there, which is essentially measured by Q33. All right. Now, when we did the numerical experiments to test for stability, we found that, yes, indeed, when you perturb the mountain, it is not disrupted, and the quadrupole saturates to a non-zero value. But in addition, and with hindsight this should have been expected, but it wasn't, in addition, we find that the mountain oscillates. And that makes sense. Magnetic field lines, remember, are like elastic bands in some sense. And so you have these field lines frozen into the material. They have elastic properties. If you move the mountain to one side across the pole, it's going to slosh back and forth with the restoring force provided by the Lorentz force in the bent magnetic field lines. The details of the oscillations are interesting. They're a mix of alphane and acoustic waves. And I have a movie here to show you what the oscillations looks like. So what we're seeing here is exactly the same diagram I showed you before. The equator here, sorry, the pole here, the equator here, altitude in this direction. Dashed curves are density contours. So you can see the mountain at the pole. Magnetic field lines are solid curves. And what I'm going to do is show you a movie where we tweak that equilibrium configuration and then just let it run. Hopefully you can see that. Yep. And so as I said, the mountain oscillates, and it oscillates in a fashion which is essentially wobbling back and forth across the pole. The frequency of the oscillations is quite high. It's the inverse of the alphane crossing time at the surface of the neutron star, which can be as high as kilohertz or hectohertz. It depends on the strength of the magnetic field. That has the effect, if you then look at the gravitational wave spectrum produced by this mountain. Here we see the plus and the cross polarizations as a function of frequency. We have the two main peaks at f star and the spin frequency and twice the spin frequency just from the bulk rotation of the mountain. But we then also have these side bands which correspond to the modes in this oscillation. Now, that's very interesting from a LIGO point of view, because if you could ever detect these, you would have direct measurements of the magnetic field strength and even the geometry of the magnetic field near the surface of the star. You'd also have a good estimate of the density at the relevant layers at the surface of the star. So having these is great. Unfortunately, it's completely unclear how strong they would be in any realistic situation. And here, to draw these plots, we made them at about, I think it was a few percent, 5%. Dimensionless amplitude, but they could be a lot smaller than that because, of course, there's a lot of dissipation in the system as well. So I just point this out as an interesting possibility, but it's completely unclear at the moment whether, in real terms, they would be detectable or not. I won't spend any time on this slide except to say that from the details of the lines that you see in the gravitational wave spectrum, you can, in principle, pull out all components of the moment of inertia tensor and also, if it is precessing, an estimate of the wobble angle. Okay, now let me show you briefly some snapshots from the second experiment. This is now the case where you do have some resistance in the problem. And in fact, to show you what happens, I've chosen an artificial case where the resistance is huge, trillions of times larger than in a real neutron star. In fact, the diffusion time is only 10,000 times the Alfvén time in the system. And what happens there, as you would expect, is that the mountain quickly relaxes away. We're looking here at subsequent times. You get initially the growth of the Parker instability I showed you before, and then at these toroidal kinks that you see in the equatorial plane here, these white points, you get strong diffusion, and the field just dies away, and the mountain, which is present initially, just spreads to cover the entire star. Okay. In real life, for realistic parameters, diffusion time is 10 to the 20 times the Alfvén time. And so you need to wait 10 to the 10, 10 to the 11 years before this happens. And this diagram makes the same point. So now we're looking at the ellipticity, the quadrupole moment, as a function of time in units of the Alfvén time for several different resistivities. Here is the realistic one at the top. You can see that you just relax due to the Parker instability and then stay constant at about 40% of what you started with. But again, if you increase the resistivity, you get progressively more and more diffusion, and this is the case that we saw in the snapshots before, where the ellipticity dies away quickly. Okay, so let's take stock. What have we got here in terms of the quadrupole, which is, of course, what we care about for LIGO? If we start with a perfectly conducting two-dimensional mountain, we get very large, for realistic accreted masses, we get large quadrupoles. However, the 3D Parker instability reduces this by about 30%. The resistivity reduces it by about 50% over 1 billion years, and by a lot more over 10 billion years. So the age of the system is kind of critical there, as you would expect, because there's an exponential, it's a diffusion problem, so it dies away exponentially. And then an issue which I haven't discussed at the moment because we haven't yet solved it, it's quite tricky. The question of sinking. For calculational reasons, we've built all of the mountains that I've shown you so far on a completely rigid, solid neutron star surface. And while that won't affect the overall magnetic geometry very much, it does affect the densities that we get near the base of the mountain. They are, in fact, artificially high by a very large factor. What you really would like is to build your mountain on a realistic neutron star crust, which, of course, would sink under the weight of the material that has been added. So you get the isostasy like mountains on the Earth. And Carl Vetter has started doing some simulations which get at that. There are numerical difficulties which I won't get into that make it tricky, but he seems tentatively to be finding that if you allow the mountain to sink, then the overall quadrupole will be reduced by a factor of 4. So if you multiply these factors together, then in the most pessimistic case, you get a quadrupole moment of 3 by 10 to the minus 9. But for a more sensible, more realistic age for these systems, you can get a quadrupole which is substantially higher. Okay, will LIGO see it? Well, we already have some limits on that from the Bilston argument and from the plots that I showed you before that Anna Watts and Badri Krishnan made based on current X-ray observations. But this now turns it around and says, well, what would our mountain model taken in isolation predict for detectability? The diagram you're seeing here is the wave strain and in the usual units as a function of spin-free or wave frequency. And plotted on top of it are noise curves for 14 days of coherent integration. The diagonal lines correspond to the mountain signal for 10 to the minus 8, 10 to the minus 7, 10 to the minus 6, all the way up to 10 to the minus 2 solar masses accreted. And the solid is two-dimensional mountains the dashed is the more realistic three-dimensional ones which have relaxed. Above 10 to the minus 6 solar masses, I shade it in green to exclude that region because at this point, ohmic diffusion starts to become significant. Once you've added 10 to the minus 6 solar masses, you add more material. Ohmic diffusion at the smallest length scales allows that material to slip through the field lines. And so while you don't disrupt the mountain that you already have, it doesn't get any larger. So this is all blocked out. And then this is blocked out simply because we've not seen any objects spinning faster than 700 hertz, or twice that, 1.4 kilohertz. And so there's a little sliver here where one might hope that these magnetic mountains would be detected by advanced LIGO. Now, the detection estimate here is made assuming you know the spin frequency in the orbit. Not always true for things like Scorpius X1. Signal-to-noise ratio is calculated this way using the single template value for this F factor with a 1% false alarm and a 10% false dismissal rate. None of these estimates take into account the effects of dephasing between the electromagnetic ephemeris and the putative gravitational wave signal. That dephasing can happen in many ways. Spin wandering, which is endemic to these accreting neutron star sources. You see it all the time. Precession, which again you might expect to see, and the oscillations of the mountain that I talked about before, which, although they're kind of cool, have the effect of jittering the gravitational wave phase in a way that would be unhelpful if it's too large. Okay, now I promised I would mention, as I said, we haven't in the past done data analysis at Melbourne, although the students are definitely interested in getting involved in it, which is why I'm here, among other reasons. But we have got one project started, and this is led by Badri Krishnan at the Albert Einstein Institute and my student Christine Chung. They are doing a radiometer search for accreting millisecond pulsars. And as you know, that involves correlating the signal between the two interferometers, so you don't actually need a matched filter in that case. For this audience, this is superfluous. I'm sure they've taken the short time Fourier transforms, made the assumptions of a constant beam and small Earth Doppler shift, and then multiplied them appropriately along the diagonal. The status of this search is that the code has been implemented, is now being tested, and the target will be put on the cluster probably early in the new year with an expected sort of first results around March or so. Okay, now let me finish by mentioning a couple of astrophysical things. One of the things, of course, that we're all looking forward to very much is that when advanced LIGO finally sees something, we'll be able to use it to infer things about astrophysics. And there are a few interesting applications, even just of this magnetic mountain idea, which I want to draw your attention to. The first one is precession. Now, if you have, as Lars Bilston inferred, a quadrupole of 1 part in 10 to the 8, and a spin period of a few milliseconds, as is typical for these sources, then you should expect precession over days. Right? And it's kind of an abiding puzzle that these precessions have never been seen. Neutron stars don't precess, even though accreting neutron stars are constantly being pummeled by torques just from the accretion. It's very well known just by looking at the X-ray signal that the accretion is variable and fluctuates and very complicated. Simulations also bear that out. You would think that during all of that there would be off-axis torques in the system that would sort of kick the neutron star around and cause it to precess. So we went looking for that. And in particular, we looked at this source J1814, which to the eye, when you look at the X-ray signal, appears to have long-term oscillations. So what you're seeing here in the left-hand panels are the X-ray flux, the width of the X-ray pulse, and the centroid, the phase of the centroid of the X-ray pulse, all as a function of time in days. And just to give you an idea, that from here to here is 50 days of data during one of these outbursts. And what you see there is sort of an oscillation, let's say. This is after folding the pulses, the millisecond pulses, over this sort of length of period. And you can run this data through a lone periodogram to look for a periodic signal, and sure enough, you see something of moderate significance, not great significance, but moderate, at about 12 days, which is exactly what your eye would have told you. You can then refold the folded data on this 12-day period to look at the same quantities, mean flux, width of the pulse, and centroid face of the centroid of the pulse as a function of the so-called precession phase over this 12-day period. And you see some, what appear to be some oscillations. Now, that's kind of interesting, but I regret to say that when we tried to fit this to a standard free precession model with either a biaxial star or a triaxial star, and with either one or with two hotspots, X-ray hotspots on the surface, we're only ever able to simultaneously fit two of these quantities. The third one doesn't come out. Now, it's not clear what that means. It could mean that one or two hotspots is just an oversimplified model for the X-ray emission on the surface of the star, and if you have a more complicated model, you do get a good fit. Well, of course, if you make the model more complicated, eventually you're going to get a good fit, so we haven't pursued that line of work any further. The other possibility is that the precession is driven, and so the free precession model is not quite right, but even there it's not clear. So it's not clear whether we've seen precession in this object. You will only get perfect fit to all three, or a good fit to all three, if the thing is almost pole-on, which is a priori unlikely. So if we discard that possibility, then there are two conclusions we can draw. Either it's precessing, and our intensity, our surface map, is not very good. If that's true, then we can place a limit on the quadrupole for this source of 3 × 10⁻⁹, which is too weak for LIGO to see, advanced LIGO. Or the modulations are not precession related, and if that's true, then you have a limit on the size of the wobble angle of any small precession that's there, and that limit comes out such that that product is less than 6 × 10⁻². And that might indicate that there's strong dissipation in the star, which is expected, but it gives you some limit on how strong that dissipation is. Okay, so what sort of things, again, can LIGO teach us? Well, as I said, the mountain oscillations tell us about the surface magnetic field if we see them. The size of the mountain is determined by the resistivity of the star, and this is of interest to condensed matter physicists as well as to astrophysicists. If there is precession that you can detect, you get some idea of the seismicity, the strength of the excitation mechanisms as compared to the viscosity, the dissipation mechanisms in the object. And that, in turn, can be inverted to tell you interesting things about the physics of bulk nuclear matter. Just to show you that we're actually quite close to getting interesting limits on these things, what we're looking at here is, please ignore this, it didn't come out properly, but it's okay. What we're looking at here is a plot of the conductivity as a function of temperature. And I'll now explain to you how this plot was constructed. What we did was take several pulsars, binary millisecond pulsars, which are no longer accreting, but had accreted once in the past. And we said, okay, let's suppose that our model gives a correct estimate for the size of the mountain initially. How resistive does the material need to be such that the mountain shrinks sufficiently such that the gravitational waves that it is emitting now are small enough to not violate the spin down that is actually observed? Okay. I'll just say that again. Sorry, because it's a bit complicated. Today we see an electromagnetic spin down from these objects. So we know they're losing energy at some rate. that has many possible causes, one of which is gravitational waves. So the observed spin down gives us an upper limit on the rate at which these objects are emitting gravitational waves. Therefore, it gives us an upper limit on their quadrupole moment. If we start with a magnetic mountain that we've calculated, then there is a minimum resistivity that you need such that that mountain shrinks below the maximum quadrupole moment that you've inferred from the spin down. Okay? And that's what these upper limits show here for several objects. The curve is the electron-phonon conductivity that you find in the literature for neutrons, for the upper layers of a neutron star. Even though it's logarithmic, you can see that it's getting quite close. We can't yet use LIGO upper limits for these plots because they are somewhat higher than the spin-down limits from these objects. But eventually, of course, LIGO will start to crowd down here as well, and you'll get corroborating evidence. The temperature axis here, I won't go into the details of how it was estimated. It's very crude. The main thing was to just get a sense for how the conductivity varies with temperature and also how that limit varies with temperature. Okay, now, if I have 2 more minutes, I just want to make 2 more points, again, on astrophysics. There's a very interesting object which has been studied by Deepto Chakrabarty and his group at MIT, J1808. It's one of these bursting sources. And what they have done is measure the spin evolution of that neutron star over when it is in quiescence. So what you're looking at here is over many, many days, 3,000 days. And the bursts are very short. But during each burst, you can measure a spin period. And then you can ask what happens to that spin period over time. And what Deepto and his student Jake Hartman found was that it decreases over long time at this rate, 5 × 10⁻16 hertz per second. Now, for an accreting object, that's quite surprising. Right? Accretion adds angular momentum, and so the star should spin up, not spin down. So, Deepto and Jake inferred that what we must be seeing here is the electromagnetic spin down of the star when no accretion is occurring, and from that they put a limit on the magnetic field. However, there are some problems with that, the main one being that when you have accretion, even a little bit, you're going to disrupt the magnetosphere of the star. You no longer have a light cylinder in the classical sense, and therefore the ideas of electromagnetic spin down are modified greatly. An alternative possibility, though, is that what we're seeing here is direct evidence for Lars Bilston's stalling idea. Because even though the accretion is slow in between these outbursts, it's not zero. And if you're accreting material slowly, then your mountain is getting bigger and bigger. And so the balance frequency, where the gravitational wave torque matches the accretion torque, is slowly going to decrease. You've got a larger mountain, so you don't need to spin as fast to have that balance between radiation reaction torque and accretion torque. And when you put in the numbers, it turns out that you get something pretty close to this. So that's interesting. It's not conclusive. It's interesting. A second little point I want to make is, what can we say about magnetars? This is sort of a whole new subject, which I'm not going to go into now. But there are a class of neutron stars which have much stronger magnetic fields than all the others, 10 to the 15 Gauss. And you can ask how big a mountain you would get if those neutron stars accreted. It turns out that the answer is huge. Their quadrupole moment is 1 part in 10 to the 2. Now, unfortunately, these objects are spinning much slower and much more slowly as well. They have spin periods of seconds. So you win a lot here, but your wave strain, which is proportional to the square of the frequency, also goes down. When you multiply the two effects together, you find that they could be interesting alternatives to the accreting millisecond pulsars as well, but a lot more work is required to firm that up, and we're engaged in that at the moment. So, in conclusion, the best calculations that we have of these magnetic mountains so far, and I want to emphasize, although we're doing it in a very idealized way, it is a first principles calculation, especially the first one, which assumes perfect conductivity. Within that context, that calculation is exact. These calculations predict stubbornly large quadrupoles, even after we allow them to relax hydromagnetically, and even after we include resistivity and allow them to relax ohmically. If they do survive at the sort of upper limit that Lars Bilston inferred from the spin period argument, then these sources allow you to do interesting astrophysics. The oscillations that I described to you, the precession, these estimates of the resistivity, all of these things are things that you can get out of a long, a 2-year coherent integration of one of these sources once you've detected it. The existing data already imply interesting limits on these various things, like the resistivity, the magnetization, and the viscosity. And, of course, there's a huge amount of modeling still to be done to get a realistic estimate, not just of the size of the mountain, but also the detailed characteristics of the signal. These things I've talked about, I haven't mentioned nuclear reactions. There's slow nuclear reactions occurring at different levels within the neutron star crust all the time. They are known to affect the kind of quadrupoles you get. Work by Ushamirski and others has shown that, and they can produce interesting non-axis symmetries of their own. Secondly, the interior of the star is a superfluid, a liquid of some sort. The complicated motions in that liquid will make gravitational waves of their own, and it's not clear whether that signal is smaller or larger than the mountain signal, and whether it's organized or noisy, and therefore will it be easy to separate the two. These are still open questions, and they touch upon some of the things I talked about at the TAPIR group meeting the other day. Thank you very much for your attention. Sorry for going over time.